In order to determine the molecular geometry for H2O, first we need to look at the Lewis structure. You can see there are two hydrogens on that central oxygen there, but very importantly there are also two pairs of electrons on the top and bottom of the oxygen in this Lewis structure. So according to valence shell electron pair repulsion theory, those four things will spread out as far as possible, and that's what's going to give us our molecular geometry or our shape for H2O. In order to visualize that, let's look at it in 3 dimensions. So here's the water molecule. We have the red, that's the oxygen, and the hydrogens are the whites, and then the lone pair electrons, they're on top. So as we look at this, we can see it's not a straight molecule. It actually has a bent shape, and that's going to be the molecular geometry, bent. Let's go back though and look at another method to determine the molecular geometry. We'll use the AXN notation to figure out the geometry. A, that's the central atom we're dealing with, in this case the oxygen. X, that's going to be the number of atoms attached to the oxygen. We have the two hydrogens, so we're going to put a 2 here. And N, that's the non-bonding electron pairs. We have 2 pairs. We have one here, and we have one right here. So N is going to be 2 as well. You could have memorized that AX2N2 has a bent molecular geometry. Or, if you have it available, you could look it up on a table. So here in our table, we go down, we see AX2, AX3, all the way down AX6, AX2N, we're getting close, and there it is at the bottom, AX2N2, which has a bent molecular geometry, and the bond angles are going to be 109.5 degrees. Going back to our 3D visualization of the H2O molecule, we can see that the bond angle between the oxygens and the hydrogens is 109.5 degrees. So using both the valence shell electron pair repulsion theory and using the table where we look at the AXN notation, we've figured out the molecular geometry for water. This is Dr. B, and thanks for watching.